time to start now. First of all, I want to say thanks a lot, Julie, for joining us today for this project, ECRISC 2050 MOOC series. I'm super glad that you accepted my invitation and that we had such really nice talks already and discussions. And yeah, I'm really curious about the next hour, what you will tell us about your research work, and also maybe a bit about your personal journey as being a PhD in the past. Yeah, I don't want to tell too much. I've sent around some background info about you already to the people before, that you're also dealing with multiple stressors in a climate change context. And yeah, I'm just very happy to have you here on board. I told you already how we will proceed in this MOOC, yes. so you know what will happen. And yes, that's why I want to give the floor to you now.
Okay, thank you. I'm also happy to be here and to present some things of my PhD. So I will talk mainly about pesticides and how they can become more toxic under global warming. So I will give a short introduction. I will also give some example studies of our research group about warming and toxicants. Then I will give some studies of my PhD. I will give some conclusions and then the acknowledgements, and then I will talk a little bit about my PhD experiences. So freshwater ecosystems are often exposed to multiple stressors, and on the one hand, we have global warming, of course, and there are different aspects that we can include in studies. For example, first, an increase in mean temperature, but also heat waves because they're becoming more frequent and also in a bigger magnitudes. So it's also important to include these. And then as last, also daily temperature fluctuations. So how temperature fluctuates in a day. And it's also predicted that they will increase under global warming. On the other hand, of course, can these ecosystems also be exposed to pollutions? For example, to pesticides, but also to pharmaceuticals or metals. So if we are first talking about global warming, everyone knows that the world is warming. Here you see an increase in mean temperature from the 1800s till now. And you really see how temperature is changing. So it's really crazy, actually, if you look at this little movie. And in the end, it will already be almost an increase in average temperature of 2 degrees. And it will further increase until 4 or even more degrees in temperature. So it's really crazy, actually. And why is the world warming? Well, yeah, because of the greenhouse effect, but I don't think I need to explain it here. But it's mainly because of the increase in carbon dioxide in the atmosphere, because it's nicely corresponding to the increase in mean temperature. So the Intergovernmental Panel on Climate Change also set up different global warming scenarios depending on the emissions of carbon dioxide. And in my studies, I focus on the representative concentration pathway 8.5. And this scenario is actually a worst case scenario that predicts a global mean increase of 4 degrees by 2100. And this will happen if we do nothing about the emissions. So if we keep emitting like we're doing now, so it's really the worst case scenario. Then another important part, like I said before, are daily temperature fluctuations. When I started my PhD, I found these 2 studies of Pymans and Vasseur, and they really showed that actually the variation in temperature in a day can make ectotherms more sensitive to climate change, and that it poses a greater risk even than only the mean increase in temperature alone. So this got me inspired already. An important rule when you're studying daily temperature fluctuations is Jensen's inequality. So here you have a thermal performance curve which gives the relation between performance and temperature. And the performance increases non-linearly and exponential until the thermal optimum with increasing temperatures, and then drops very fast to the critical thermal maximum where performance is 0. So when you have a constant temperature, for example, the green dot, your performance equals this in the second figure. However, when you have variation around this temperature in a day, so it goes above and beneath this temperature, you see that when the temperature increases, that this increase in performance is bigger than when the temperature drops beneath this temperature. So actually, the net performance is higher when you have variation than when you're constantly on the green dots. However, of course, this also depends on where this temperature is situated on the curve. So for example, when this temperature equals your thermal optimum, so where performance is optimal, it will be, of course, better to stay constantly on this temperature than when you have variation around this temperature, because then your performance will drop at both sides of the curve. So your net performance will be less when there is variation than when you're constantly on the thermal optimum. And you even can go further. So if the temperature is beyond the thermal optimum, this will be even worse because of the rapid drop in performance when you're beyond the thermal optimum. So this is even a worst case scenario. Then on the other hand, you have pollution. So freshwater ecosystems can be exposed to pesticides, for example, via spray drift, so directly, but also indirectly via the wind, and also via runoff. And this can cause mass mortality events. So it's actually quite bad. As for example, Beckett et al. Showed, they even showed that pesticide concentrations that were considered as environmentally safe by the government, that they caused a really big drop in regional biodiversity, and even with losses in taxa up to 42%. So it's really important to find ways to actually improve the risk assessment for pesticides, but also, for example, for pharmaceuticals. Then pollutants and global warming can also interact. So they are also both these stressors are identified as two areas of concern for environmental impacts by experts in the European CETAC Horizon Scanning Workshop. And it's also nice because these two stressors has also been discussed, that there are two concepts linked to these two stressors. And first is that if you have higher mean temperatures, the toxicity of pollutants can increase. For example, for the pesticide chlorpyrifos. And this is called the climate-induced toxicant sensitivity, or the CITS concept. I will always use the abbreviation because it's a long term to pronounce. And why is this happening? It can be because of multiple reasons. First, for example, higher energy costs are linked to both stressors. When you have a polluted site, for example, your energy demand will be higher because you have also a detoxification cost. When your site is only heated, you will also have a higher energy demand because your basal metabolism is higher. But when you have then both stressors present, your energy demand will be quite high, so some organisms won't cope with this. And that's why, or this is one of the bases of this concept. At the other hand, at the higher mean temperature with a higher metabolism, it's also possible that they take up more of the pesticides, and that this pesticide is more metabolic converted to the more toxic form, like for example, for chlorpyrifos, it will become chlorpyrifos oxone, and this is 100 times more toxic than the original compounds, and it interacts more strongly with its target enzyme acetylcholinesterase. On the other hand, when you're exposed to a pesticide, this can also decrease the heat tolerance, or which is often measured as the critical thermal maximum. And this is the toxicant-induced climate change sensitivity, or the TICS concept. And why is this? So when you're exposed to a pesticide, you can again have these higher energetic costs that organisms need to invest more energy in defense mechanisms. But pesticides can also impair the respiratory functioning, which will then result in a decrease in oxygen uptake. So both these mechanisms cause that the mismatch between oxygen supply and demand will happen at lower temperatures than when you're not exposed to a pesticide. So you will get this shift of CTMX to the left. Then both concepts can also be coupled. So when you have higher mean temperatures, the toxicity of pollutants can increase. And because of this higher toxicity, this can result in a more stronger decrease in heat tolerance. So now I will give some examples. So first, some examples about higher pesticide toxicity that has been found under higher mean temperatures. So this is a former colleague of us, Quang Dim Van, and he studied it mainly in Damselfly larvae, in this case, Ischnura elegans. And he combined exposure to warming plus 4 degrees in mean temperature and the pesticide chlorpyrifos. If we look at results, this is for survival. We saw in the left panel no pesticide effects on survival, so at 20 degrees. However, at 24 degrees, at the highest chlorpyrifos concentration, we saw a reduced survival. And actually, we saw also the same pattern happening in growth rates. However, here the pesticide also decreased growth rate already at 20, but it was stronger at 24 degrees. So this is actually already evidence of the SIDS concept. Then another example are with Culex pipiens mosquito larvae. Here they combined both the studies, warming again the plus 4 degrees mean temperature and the pesticide chlorpyrifos. In the left study of Vienna Donat, we see the results for survival again, and we see that there was a synergistic interaction between mean temperature and the pesticides. So at 24 degrees, the reduction in survival by chlorpyrifos was stronger. And this was also happening in the study of Tran et al., where we saw a small pesticide effect at 20 degrees, but again, it was way stronger at 24 degrees. So again, these are in line with the SIDS concept. Then we shift to another part of this talk, if pesticide toxicity would increase after a heat wave. So it's again in Damselfly larvae, but now in another species, in Sunaigion cruella. And Quang first combined exposure to a heat wave of 30 degrees and food limitation, as it can both happen at the same time, because it's often that mass mortality events happen during heat waves in freshwater ecosystems. And then he combined it with a second exposure to a pesticide, chlorpyrifos. So for the results for survival, we really saw a strong reduction in survival when animals were exposed first to a heat wave and to food limitations. So they were starved, and then afterwards to chlorpyrifos. And it was nice to see that he also found the same thing on the physiological level for phenol oxidase activity for the immune function. So it's really nice to see that it's happened both at the life history trait and in the physiological trait. And this is again in line with the SIDS concept. Then a cool study that was recently out, done by colleague Shang Dong. I really think this is a cool one. He studied Culex pipiens mosquito larvae, and he exposed them in the final larval stage, the L4 stage. And he exposed them both to a heat spike and chlorpyrifos. But the cool thing here was that he changed the order. So first, he exposed some larvae to first the heat spike and then to chlorpyrifos. And in the other part of the experiment, he exposed them first to chlorpyrifos and then to a heat spike. When we look for the results, so here it's first exposure to chlorpyrifos and then to the heat spike. So we see that mortality increased with chlorpyrifos concentration, but that it was more strongly when they were exposed to a heat spike afterwards. So this is in line with the ticks concept because chlorpyrifos, the chlorpyrifos exposure was first. When we look at the other way around, so first the heat spike and then chlorpyrifos exposure, we also see an increase in mortality with increase in concentration, but it was way more pronounced when they had first a heat spike. So this is in line with the SIDS concept again. So here it was cool that the exposure order modified how the heat spike increased chlorpyrifos toxicity, and that they found more stronger synergisms between the heat spike and chlorpyrifos when chlorpyrifos was applied after the heat spike. So actually, we can maybe say that SIDS plays a more important role, but yeah, more studies need to be done on this, and I think it was pretty cool. Then we go to the third part, so how pesticide toxicity increased under daily temperature fluctuations. And this is actually one of the first studies, I think, that combines daily temperature fluctuations and pesticides. And I also based my PhD a bit on this paper, so it was really an inspiring paper. And Wilming et al. Used Hieronymus dilutus match larvae. And it was cool to see that the pesticide bifenthrin was more toxic, so caused a lower survival when DTFs were present. So it was quite cool. And two other studies also linked to this DTFs that increase the pollutant toxicity, or these two. But there are not so many others, so I was really inspired to do something with this in my PhD. So then, this is the first article for one of the first of my PhD, and I wanted to know if the pesticide toxicity was higher in the DTFs. So I used 3 DTF levels around 20 degrees. So here the 0 degrees DTF is actually just 20 degrees constant, so there is no fluctuation. When there's, for example, 10 degrees DTF, temperatures drop till 15 degrees and rise till 25 degrees in one day. I use the pesticide chlorpyrifos, 2 concentrations, and then I used high latitude populations of Ischnura elegans tensorfly larvae. So I used a typical organophosphate, chlorpyrifos. This pesticide inhibits the enzyme acetylcholinesterase, which plays an important role in the nervous system. It is used worldwide, and it is a top 10 chemical with one of the highest risks to freshwater ecosystems. But it's also recently banned from January in Europe. So it's still used in the United States and I think Asia and Australia, but in Europe it's forbidden. In the experimental design, so I reared my larvae in climate chambers, and then when they became final larval instar, I exposed them to one of the 3 thermal regimes. After 7 days of acclimatization, I exposed them to one of the chlorpyrifos concentrations for 6 days, and I also daily renewed the medium. I looked at endpoints, for example, mortality and growth rates, and later on we did also some physiology. So some results. First, for mortality. So here for the solvent control, we didn't see any effects of the daily temperature fluctuation or mortality. When they were exposed to chlorpyrifos at just 20 degrees constant, we also didn't see any effect on mortality. So this could actually be considered as a no observed effect concentration. However, when we included TTFs, mortality increased almost by 3-fold when they were exposed to chlorpyrifos. So yeah, this was a really cool result. We also saw the same for larval growth rates. So in the solvent control, nothing was happening. So DTF didn't influence the growth rate here. Also not when they were exposed to chlorpyrifos at 20 degrees constant. But again, growth rate really decreased even to negative values when they were exposed to chlorpyrifos under daily temperature fluctuations. So these daily short-term exposures to higher temperatures cause a really higher pesticide toxicity. And why would this be happening? Well, I guess because of the reasons I gave already in the introduction when explaining the SIDS concept. So because of a higher metabolic rate at higher temperatures, you can also have a higher uptake of chlorpyrifos, also a higher metabolic conversion of the original compound to the more toxic metabolite, in this case chlorpyrifos oxone, and because of the higher energetic costs when you're exposed to both stressors. What we didn't see is interaction effects on the physiological level, but this is maybe to do with the higher mortality under these conditions, so that survival selection maybe had an effect here. I also inspired other colleagues to work with DTFs, and I was very happy about this. Like Vienna, she also used this in a study with Culex pipiens mosquitoes. She studied both the larvae and the adults, but I will focus here on the female adults. And she combined exposure to daily temperature variation or fluctuation and a pesticide chlorpyrifos. So if we look at the results for CTMX, she showed that there was no chlorpyrifos reduction in CTMX at 20 degrees constant, but there was a strong chlorpyrifos-induced reduction in CTMX at 20 degrees when we included daily temperature variation. So this was also quite cool. In my following studies, I combined even more. Like I tried to combine a mean temperature increase, an increase in DTF level, and exposure to a pesticide. And I raised the following questions before starting. So first I wanted to know if the 4 degrees warming and 5 degrees increase in DTF would magnify the chlorpyrifos toxicity, so which is actually in line with the SIDS concept. Also, if chlorpyrifos exposure would decrease heat tolerance, or the CTMX, which is in line with the TICS concept. I then wanted to know if also these two concepts would be coupled, and if gradual thermal evolution would buffer for the increased chlorpyrifos toxicity under global warming. But I will explain this a bit further. So the study species I used in the following studies was Ischnura elegans, the blue-tailed tensorfly. And I used both high latitude populations situated here in southern Sweden and Denmark, and low latitude populations of southern France. And important to know is also that they differ in volatinism. So these populations have actually just one generation every 2 years. So it's actually semi-volatile, while these are multi-volatile and have multiple generations each year. Plus, it's also a fact that they are thermally adapted. So they're thermally adapted to a mean summer water temperature of 24, and they experience a maximum DTF in summer of 10 degrees. While in the high latitude populations, this corresponds to a mean temperature of 20 degrees with a maximum DTF of 5 degrees. And in the IPCC scenario, the worst case scenario, RCP 8.5, it's also predicted that the current situation of France will become the future in Sweden. So this is why we could apply a space or time substitution. So here you need actually a time gradient. So for example, the IPCC that predicted a higher mean temperature of 24 degrees and also a higher DTF of 10 degrees. And this time gradient corresponds to the latitudinal thermal gradient, like I said before. the low latitude populations are adapted to a higher mean temperature of 24 and experience a higher DTF of 10 degrees, while for the high latitude populations, this is 20 and a low DTF of 5 degrees. So by applying the space versus time substitution, we can actually predict what will happen in 2100 if larvae would be able to thermally evolve. So if you have the low latitude populations and their reaction to this high mean temperature and high DTF, you can actually use it as a proxy how the high latitude populations will do under global warming by 2100 if they would be able to thermally evolve. So if they actually would become French populations. However, you can also just expose the high latitude populations to this higher mean temperature and higher DTF, and then you can consider the plastic response. But this is more a shock approach. Furthermore, I also included now an additional stressor, the pesticides. And with this, we can actually predict plastic and evolutionary responses of these high latitude damselfly populations to pesticides under global warming. So my experimental setup here, so I used 6 thermal regimes. So the 2 mean temperatures, of course, and the 3 levels of DTF. I also included the constant one. So this is the 0 degrees DTF. And I used 2 chlorpyrifos concentrations and, of course, the 2 latitudes, so the 2 latitude populations of Ichneumon. The experimental design then. So 10 days after hatching, I started wearing them at one of the 6 thermal regimes. And then 1 day after they become the final instar larvae, I exposed them to either a solvent control or the chlorpyrifos concentration for 6 days, and I daily renewed the medium. In this period, I daily checked mortality and also calculated the growth rate. And afterwards, I did a CTMX trial. So let's see. So we put them in these small containers with water in a warm water bath, and the temperature will rise then with 0.3 degrees per minute until they faint. So you will see it in a couple of seconds. So we gently tap them to see if they are fainted or not, because sometimes they still show some muscular spasms. And when they're fainted, we take them out and we let them recover at room temperature to see if they are still alive, because if they died during the tests, you went too far with the CTMX, so then they are excluded. So for the effects of the stressors, first on mortality. So to be clear, we have here different panels. So first for high latitude on the left side and on the right side for low latitude, and it's always for 20 degrees, 24 degrees. On the x-axis, it shows the pesticide concentration, and then the bars colors are the DTF differences. So here we see that chlorpyrifos induce mortality, which was expected. And we also see in most cases that 10 degrees DTF increase the chlorpyrifos-induced mortality. Furthermore, when we look at the mean temperature, we see that 24 also increased chlorpyrifos-induced mortality, but only for the high latitude larvae. So both these results are in line with the SIT concept. Also, for the low latitude, we didn't see this pattern, so this could be a sign or a signal for local thermal adaptation. As they are adapted to higher temperatures, they may have more energy to cope with chlorpyrifos, as their basal metabolism is already higher than in high latitude populations. Then for the results on CTMX, so chlorpyrifos reduced CTMX, which was in line with the TICS concept. We also saw that this was stronger in most cases at the high DTF level. So this is actually the coupling between the SIT and the TICS concept. As we also saw that high TTF increased the toxicity in terms of mortality. So the toxicity was higher, so the reduction in CTMX was even stronger at the high TTF level when exposed to chlorpyrifos. Then we had also a four-way interaction, but I will help you through it because it was also not so easy for us to interpret this four-way interaction. But first, so I will start in the left panel. For the high latitude at 20 degrees. So the chlorpyrifos-induced reduction in CTMX was only present at the high TTF level of 10 degrees. At 24 degrees, however, this reduction caused by chlorpyrifos in CTMX was across all DTF levels. When we then go to the low latitude larvae, it was actually the opposite. So this general reduction caused by chlorpyrifos in CTMX was across all DTF levels. And at 24, it was again only at 10 degrees DTF. So it's actually a nice switch, which leads to our conclusion that local thermal adaptation might have buffered for the chlorpyrifos-induced decrease in thermal tolerance, as low latitude larvae are adapted to the higher mean temperature. So only there was a decrease in CTMX caused by chlorpyrifos at 10 degrees CTF, while for the high latitude larvae, it was at 20 degrees. Then if we consider what will happen with the high latitude populations under global warming by 2100, so we here see the results without TTFs, so we only consider the mean temperature increase. If we then look when they would just react plastically, so we have the current situation on the left and the future situation on the right, the high latitude populations would suffer a chlorpyrifos-induced reduction in CTMX. When they would be able to thermally evolve by 2100 and actually become French populations, they would no longer suffer an chlorpyrifos-induced reduction in CTMX. However, when we include TTFs, this is no longer the case, because then if they would just plastically respond or under thermal evolution, so if they would be able to evolve into French populations, they would in both cases suffer a chlorpyrifos-induced reduction in CTMX. So from this study, it's really actually important to include TTFs to make your study more realistic, because it's also happening already now that there are high TTF levels present across latitudes or even big differences. So, yeah. And in the second part, actually the first question is the same as my previous part, but here I wanted to focus more on if larvae would shrink under global warming, so in line with the temperature size rule. Also, if these smaller larvae would be more sensitive to chlorpyrifos, and what the underlying physiological mechanisms were. So it's already known that under daily temperature fluctuations, but also at higher mean temperatures, that organisms shrink. This is because of the temperature size rule, and this states that the increase in development rate is bigger than the increase in growth rate at higher temperatures. So organisms have actually less time to grow. So this gives a smaller size at a given age. So these smaller larvae with lower total surface area have also, at the other hand, a higher surface area to volume ratio, or the AV ratio. And it has been shown that this causes a higher pesticide uptake than when organisms are bigger, so in relation to their size. And it's shown in Butchwalter et al. For chlorpyrifos. So the experimental setup is actually similar to the previous one. So I again use these 6 thermal regimes and these 2 latitudes, but I only included more chlorpyrifos concentrations to see also concentration-dependent effects. Also, the experimental design is quite similar. I only looked at also different endpoints here to determine the size of the organisms. I measured the total body surface area by measuring the body length, the head width, and the lamellae surface. And I did also physiological analysis afterwards. So some results. First for growth rate, and I only combined here the chlorpyrifos concentrations and the DTF levels. So here chlorpyrifos decreased growth rate, and it was magnified by 10 degrees DTF. Then when we compare the solvent control with the low chlorpyrifos concentration, we see first in yellow that chlorpyrifos did not reduce growth rate at the constant temperature. However, it did at 5 and 10 degrees DTF, which is again in line with the SIDS concept. So when you include DTFs, that chlorpyrifos becomes more toxic. Then some results for mortality. So here you see a panel for 20 and 24 degrees with 2 chlorpyrifos concentrations. So we see that DTF increased mortality, especially at the high DTF level. And this was also magnified at the high mean temperature. So for example, for medium CPF, we saw that the 10 degrees DTF increased mortality, but it was only present at 24 degrees. When we look at high CPF level, we see that 10 degrees DTF increased mortality, also at 20 degrees in the left panel, but it was really more pronounced at 24. And it was already occurring at 5 degrees DTF. So again, these results are in line with the SIDS concept. If we then go back to the results for the temperature size rule, so if they got smaller in their warming, we see first with DTFs in red indicated that both high and low latitude larvae became smaller in the DTFs, both at 20 and 24 degrees. For the effect of the mean temperature, we only see the 24 degrees total surface area at the high latitudes, so only in high latitude larvae. Then we wanted to know if smaller larvae also had a higher surface area to volume ratio. So here we see actually one dot is one larvae from the experiment, and we see that the smaller larvae, so with a lower total surface area, have a higher surface area to volume ratio. So we now wondered if they would take up more pesticides, and especially because we didn't study the pesticide uptake in C, but we studied if they were more sensitive to the pesticides. So here we show some correlations between life history traits and total surface area. So the upper panels are for mortality and the lower panels for growth rate. The two left panels are the solvent control treatments, and then on the right panels we have the chlorpyrifos treatments. So the total surface area, there are also clusters per group. So we really see when chlorpyrifos is present, that smaller larvae indicated with the red circles have a higher mortality than big larvae, but it's not happening in the solvent control, so only when they were exposed to chlorpyrifos. Plus, we also show this for growth rate, but then the opposite pattern, that smaller larvae have a smaller growth rate, but only in the chlorpyrifos exposure, so that they suffered more from the chlorpyrifos exposure. When we then go back to the growth rate figure, so that's here, chlorpyrifos was more toxic in the high DTF levels. We now included and extended this model with total surface area. And then we saw that DTF, or this interaction between DTF and chlorpyrifos, was no longer significant. So here we can actually say that the higher chlorpyrifos-induced reduction in growth in the high DTF was actually explained by the decrease in total surface area at high DTF. Then we are near the end. So I also wanted to know which underlying physiological mechanisms which could explain this increased toxicity that we see under higher mean temperatures and under higher DTF levels. So I focused here on the energy budget or the cellular energy allocation, which is actually the energy availability divided by the energy consumption. So here at 20 degrees constant, we'll just give the most important results here. So at 20 degrees constant, we saw actually little effect of chlorpyrifos on the energy budget. However, when we combined the increase in mean temperature and in DTF, we saw a big chlorpyrifos-induced reduction in energy budget. And this was mainly determined by the same reductions in energy availability and not in energy consumption. So it was mainly explained by the same reductions in fat content and sugar content. Then we wanted to see the relation between mortality and energy budget and growth rate and energy budget. And here on these figures, you see actually the treatment means. And the red circles indicate actually the treatments with the highest chlorpyrifos concentration, the highest mean, and the highest DTF level. So it's actually the worst case treatments, but they cluster quite nicely. And you see, for example, for mortality, that the treatments with the lowest energy budget have the highest mortality. And for growth rate, also the ones with the lowest energy budget have the lowest growth rate. So then some conclusions. So higher daily temperature fluctuations under global warming can increase the chlorpyrifos toxicity, which was in line with CITES. Also, exposure to chlorpyrifos decreased the heat tolerance, which was in line with the TICS concepts. Those concepts are connected. However, this differs between latitudes. Also, long-term evolution to warming may buffer for the higher pesticide toxicity at these higher constant temperatures, for example, for heat tolerance, but this was not the case when DTFs were included. So both these concepts are also crucial to understand pesticide effects in a warming world and to include DTFs. So it's really important actually to make studies more realistic and to include DTFs and also the possibility of gradual thermal evolution, as sometimes a lot of results differ between latitudes, to make more important realistic predictions of effects of global warming on toxicant sensitivity in the future risk assessment, but also already in the current risk assessments, as for example, the mean temperature or DTF level are quite different across latitudes now already, and also, for example, in one latitude, if you have an urban-rural gradient. And if you want to know more, there's a recent study out, a really cool one by a colleague of mine, Charlotte. She was once my master's student a couple of years ago. And it's also about how higher mean temperatures and fluctuating temperatures impact the pesticide chlorpyrifos. And it's with Acellus aquaticus, so a freshwater isopod, to also study the effects on leaf consumption. So by this, I want to thank Robbie, of course, my promoter during my PhD and also now during my postdoc. Also all my colleagues for helping me during the experiments and with the writing process. And of course, Ria, she's here. She did a lot of physiological analysis as well, so thank you, Ria. And also Geert and Ronnie, which are not on the picture, but thank you for the technical assistance during the experiment. And also my funding, I want to thank the FWO. Then really short about my PhD experiences. So what I really liked was the field work. So we went a couple of times to France and also to Sweden to do field sampling and other things. So it was really nice, except when you got stuck in the mud, like on the picture. And sometimes it's hard because it's so hot and stuff, but it's really nice to do. And I also really love lab work. I like to be busy in the lab, running big experiments with a lot of helping hands, of course. I really like to do a lot of experiments and then some years of writing. So my PhD was also like that. First 2.5 years of experiments, and then it was only writing. Then something about statistics, because I have sometimes four-way interactions, and it was sometimes difficult to analyze, and also when you analyze it, to interpret these interactions, it was sometimes quite complex. And I had also some problems with analyzing mortality in the beginning, because I had complete separation of my data, that, for example, everything died. No, not everything died. Everything survived in one treatment. And then it was hard to analyze it. Yeah, for the writing, I also really like it to dig in literature and to write, but sometimes, it goes good, sometimes bad. But it comes with days, I guess, but it's really nice to do. I also like to go to conferences. You can really network there. So it's nice to do, especially, I think, the poster presentations, because then you can really interact with other people. While when you have a talk, it's less obvious to quote that person. And also the traveling, of course, it's nice that it comes along with that. And I also like to be part of the Hobby Stocks Lab, like the Evolutionary Stress Ecology and Ecotoxicology Lab. As we are a really good group and we're helping each other when needed, especially during these big experiments, when something goes wrong or all larvae are synchronized, that you have a lot of work during one day, you can always count on your colleagues. So that's really nice. So with this, I think I want to end, and I want to thank you as well for listening to me, and I'm happy to take any questions. Thank you.
Thanks. Thank you. Julie, thank you very much. That was a brilliant talk. It was a lot of fun to follow you, to follow your work and also your research area. I think, this was just really relevant for a lot of people actually joining this talk today. So now the idea is really to go back to the panel view and give everyone the chance to ask a question or maybe leave a comment. Yes, so I think you can kind of close your screen again, the sharing button, and then in the meanwhile, perfect. People can also use their camera, because it's always nice to see if someone has a question who's behind the microphone. And so let's open the question and discussion round. Who has a question or wants to leave a note? I know already that someone.
Yeah, I was waiting for you to give me the floor,
Yeah.
Marcus, but okay. Hey, Julie, thank you so much. That was such a great talk. So many interesting results. It's a lot. It's like crazy much information.
Thank you. Sorry.
Still processing it. I would also ask, maybe also for others, maybe we can find that out later. Like, you already defended your PhD, if I'm correct. So you already have the book, right? I would be very much interested in that.
I can send you the book. The PDF.
that would be great if that's a thing. Okay. Good. So now to my question. I personally do have a bit of reluctant about this kids and SIDS concepts, which is mainly probably because I'm not sure how it's supposed to be used. So the way that you used it, if I understand correctly, is more or less the sequence of the stressors.
Yes.
Okay. If you're looking at an endpoint as survival, I feel if you only use it as the sequential concept, it works the way you showed us it works. But by only knowing the survival, I would be reluctant to say that really one causes the other to go up or down in mortality. You know what I mean?
Yeah, I know. Yeah, it's also sometimes difficult because also when you expose them to both, for example, temperature increase, the TTF increase, and chlorpyrifos at the same time, yeah, then what has the upper hand? It's like both concepts interacting probably, but they enhance each other. So yeah, sometimes it's really difficult to separate the two concepts. That's true, yeah.
Okay, so but there's evidence that this is meant to be used as the sequential thing. Okay.
Yeah, like we discussed also a lot about
that's.
it.
I feel like if you probably looked like this comes from the paper from like about the AOP, including this in AOPs, right? And
Yes.
there you are maybe also looking at way different endpoints other than survival. So then you can really also assume that they might want to say climate-induced means that this is the driving factor and not necessarily the first. So that's why I wanted to ask how you see it. But maybe that's also to be determined in the next years.
Yeah, we're also, I think, one of the only groups that are really using it. Like there are not so much studies that use the sits and ticks concept anymore.
Maybe it needs more explanation. For me, it would need like, okay, you can say it's a sequential, but I'm not sure if that's what it's supposed to be, as in the paper it was displayed in the whole AOP thing. But okay.
I think with the heat spike, that example that I showed from Shandong, with first the heat spike, then chlorpyrifos, and then the other way around, I think it's quite clear that the order also matters and that it's two really different things. So yeah.
All right, great. Yeah, that's already that's a very satisfying answer. Thank you.
You're welcome.
All right. Another question, please. If anyone has one or a comment. Yes, Andrea, go ahead, please. Otherwise, I will just go for it. But please.
Okay, thank you very much, Julie, for this very nice presentation. I have some doubts on the methods you use for the analysis of energy on the organism. Can you explain a little bit how you did that?
So for how we measured it, or
how you measure it?
So we measured the sugar content by measuring the glucose and glycogen. I don't know how you glycogen, I think. And then we measured the fat contents as well, and we measured the protein contents to assess the energy availability. And then for the energy consumption, we measured the electron transport system activity. So it's also an enzyme, and it's a good assessor for metabolic rate. But yeah, we did it like this now. But for the really methods, I can send you because it's quite elaborate, I think, to explain everything of each physiological analysis.
Okay.
Or we can have a discussion afterwards. It's also fine for me.
Okay, no, I will be pleased if you can share these methods, because it's something completely unknown for me, and I would like to learn how to do that.
No, that's okay. I can send you it's mostly in the appendix, I think, but I can send you the whole appendix with the analysis in detail. So.
Okay, thank you.
You're welcome.
Another question in the round. Please just raise your hand or go ahead. Otherwise, I might have a short question also on the latitudinal gradient. Like when you tested the species between France, Belgium, and I think Sweden it was, right? I think
No, go on. It's okay.
I think in the beginning you showed a study by your colleague who did a similar thing.
Yes.
And I remember the bars were actually almost the same. So there was not really a difference in the latitude, right? But then later in your talk, when you talked about your work, there was. So can you maybe shortly sum up what was the reason there?
Yeah, I think it's also because sometimes you use different populations. So it will also depend on that, because sometimes they react a bit differently. So I used almost, I think, the same in my studies, but they are different from the ones that were previously used. So that's maybe a reason. But yeah, sometimes with the latitudes, it also depends. For example, if you do field collected animals, or you wear them from the beginning at the temperature, or like I sometimes do, I give them a winter first, and then afterwards, when they are 0, I expose them to the treatments. So I think, yeah, it all depends a bit, and also from the populations, of course, because if it's slightly different populations with, for example, that there are deeper ponds, then it's already a bit colder, and yeah, because we always select shallow ponds. Yeah.
Okay.
But yeah, good point. I didn't compare yet with the previous one.
Okay. All right. And then just something that we shared in our previous discussion, like us two, I was a bit nosy about your work and really asked, like, where are you going right now? Because I mean, I read your papers as well before for the ongoing research here, and you said that the extreme events will be more and more important also in your upcoming research now. Can you maybe shortly elaborate on that?
What I'm doing now, then.
Yeah.
So now I'm also looking at the adult stage. So in my PhD, I only focused on the larval stage, but now I also want to know how these effects transfer to the terrestrial system. So how they affect the adults with like emerging, but also their physiology. For example, the PFA content, important. It's an important fat content, sorry. And how this transfers, for example, to spiders. Like we have also now a spider culture, and we want to know, for example, when damselflies are polluted, affected by a pesticide and warming, how this influences the performance of spiders, for example, the egg clutch size or their growth rate. So really going from the aquatic phase, exposing them there, and then see what happens in the terrestrial stage. So that is one of the things I'm doing now, yeah.
Nice. Okay. Thank you, Julie.
Yeah, you're welcome.
If anyone else might have another question, now it's a chance. Yes, Janneke, please.
Yeah, I would also like to say it was a very good presentation, and I think you have a very important point with this, with a variation, not just looking at the mean. And this has been said by many, but you're actually studying it very, very systematically. So I think that's an important work. And then I'd like to follow up on the comment or question from Annika, because on the sequence, I was involved in that workshop where we used concepts, but back in 2013, and I really have to think now, what did we really mean? But I think what you said is correct, that it has to do with this sequence. And it was also nice to see that you are using the concepts, maybe not so many else, others are using them. But I remember also we used those concepts at different levels, at the individual level and at population community level. And then the mechanism is, of course, different. In both cases, it's there's some trade-off involved. So either a physiological based trade-off when it's at the individual level, and then at the population level, there's a different kind of trade-off. Like if some individuals are killed first by a toxicant, then the survivors might or might not be more sensitive to the toxicant. So that's the idea.
Yeah.
So that's a different mechanism. And then you have the evolutionary aspect as well,
Yeah, of
which
course.
you are also investigating. So that's very, all in all, very, very nice work.
Yeah,
So
thank you.
I didn't really have anything to correct or add to the question from Annika. It just made me reflect a bit about this concept and how we use them.
Yeah, I was like looking at your name. I was like, that's her.
Yes, and Paul was also involved in that workshop. Of course.
Yeah. Nice to finally meet you.
Yeah, likewise.
All right, we have passed 4 o'clock now, so officially we have the end of this MOOC now. If anyone has now a remaining question, I am sure you can always contact Julie via her email. I've also sent around the link to the research group. So I think it shouldn't be a problem if there are any urgent follow-up questions. So yes, then once again, I hope you all enjoyed this talk. It was way more data-driven than the talks before. I was really happy. No, I was really enjoying it. And,
yeah, that's good to hear.
Yes, and yeah, I will follow up your work, and I'm curious what you guys are doing about the DTFs and the extremes in the future.
Likewise.
Yeah. Okay.
Yeah, and indeed, if you have any questions or when you're suddenly thinking a few days later about it and you want to have Skype, you can always email me and I will make time for that.
Thank you.
And I will also send you then the PDF of my thesis, PhD thesis. Then you can send it around or
maybe
to the people that are interested.
Yeah, maybe from the ESR or also the other people, they can just send me maybe a short info if they want to have a printed version. And then we can kind of make a collection so that you don't have to send like 10 different ways or so.
Yeah, no, that's fine.
Okay. Yeah, so once again, thank you so much. That's it for today, I think. See you all.
Yeah. Okay, bye.
Bye-bye.
Bye.
Thanks again. Bye.
Thank you very
Bye.
much.